So the last section we looked at was 9.5. Skipping section 9.6, we've moved on to our parametric equations and plane curves. Now, a plane curve is a little misleading. A curve can be a straight line of motion as well as a curved motion. Parametric equations are when we use a different function for the input than we do for the output. So another way of representing curves in a plane is by using parametric equations. Parametric equations are not unique. You can write them, when you choose to write them as a single equation, you can do it in more than one way. They are also not composites. If you remember from college algebra when we did composite functions, we would take the output of one function and use it as the input for the next. That's not what we're doing. With parametric equations, we are taking the output of two separate functions and using those outputs to form our ordered pairs that we're going to graph. This first function gives us the output for the x coordinate, and the second function gives us the output for the y coordinate. Here's our definition. Let f of t, y equals f of t, and g equal, let me start over. X equal f of t, and y equal g of t, where f and g are two functions who have a common domain over some interval. The collection of points defined by x, y, which means defined by the output of f, then the output of g, is called a plane curve. The equations x is equal to f of t and y is equal to g of t, where t is time, in the interval, are called parametric equations of the curve, and the variable t is our parameter. So like I said, for these equations that we're going to be working with, t represents time, and the time is our parameter. Okay, so the first one we're going to do. Parametric equations are useful in describing movement along a curve, things like a path that a figure skater makes in doing a figure eight on ice. So that could be defined by a parametric equation. If you have a Roomba that vacuums your house, its path could be described by a parametric equation. So for our figure skater example, the input, so that's not correct. The first coordinate in my set of points, the x coordinate, is defined by the equation x of t equals 4 sine pi half t. And the y coordinate is defined by the equation y of t equals 8 cosine pi fourth t over the interval 0 to 8 seconds. So it takes our figure skater 8 seconds to complete the figure eight, and we are going to map her pathway using these equations to find our points. X of t represents horizontal movement, y of t represents vertical movement. Alright, so here we go. So we are going to plug in each value of t to both of the equations. Let's work through our x coordinates first. For our x coordinates, if t is 0, we have sine at 0, and that's just 0. 0 times 4 is 0. If t is 1, we have sine at pi half, which is 1 times 4. If t is 2, we have sine at pi, which is 0. If t is 3, we have sine at 3 pi halves, which is negative 1 times 4. If t is 4, then we are back to 2 pi. Sine is 0 there. Do you see my pattern forming here? If it's an odd number, we're going to either be at the pi half or the 3 pi halves. We've rotated around now again to the top of our graph, so it's going to be a positive 1 times 4. Then we go over to pi, down to 3 pi halves, coterminal, which gives me a negative 4, and then back to our 2 pi location. So those are our x coordinates. When we come over to form our ordered pairs, those values are going to go for the x values for where we get ready to start graphing our directed motion. So here we go. We're going to say we've got 0, 4, 0, negative 4, 0, 4, 0, negative 4, 0 is our x values. Now let's do our y values. Excuse me. So for our y values, we're plugging t in, our seconds in, to the second function, 8 cosine pi fourth t. So this one takes a little bit more work, but we are still looking at special angles, those quarter angle values. So at 0, at my very starting place, I've got cosine of 0. Well, the cosine of 0 is 1. 1 times 8 is 8. And then I move to 1, so I've got the cosine at pi fourth. Well, that's square root 2 over 2 times 8 gives me 4 square roots of 2. And if I plug that into my calculator, we're going to round that to about 5.7. Then I go, not this column. I'm not looking at this column at all. Let me just cover that up. Then I go to where t is 2. At t is 2, I've got the cosine at pi half, which is 0. Cosine at pi half is 0, yep, and anything times 0 is 0. At 3 pi fourths, cosine at 3 pi fourths is a negative pi half, so that gives me a negative 4 square root 2, which is about a negative 5.7. Then I go to 4, so that's cosine at pi. Cosine at pi is negative 1, so that is a negative 8. Then I go to 5, cosine at 5 pi fourth is still negative, so that's going to be my negative 4 square root 2. At 6, that's the same thing as cosine at 3 pi halves, and that is going to be 0 again. Then I go to 7. At 7 pi fourths, I'm in my fourth quadrant. Cosine is positive there, so that's going to be a positive 4 square root 2, so a positive 5.7. And then at 8, I'm back to 2 pi. Cosine there is 1, so my value is 8. So I can see that for my y-coordinate for these points, I follow a pattern. 8, positive 5.7, 0, negative 5.7, negative 8, that is a negative 5.7 again, 0, positive 5.7, and 8. Okay, we're going to plot our points using arrows to show path and direction. That's one thing that our parametric equations have that our other equations don't. They have direction as well as a relationship with time. So when our figure skater starts, they're at this location, 0, 8. And then our figure skater moves to 4, 5.7, so over to 4, up to almost 6, and then to 0, 0. So think about the figure skater. This is going to be a curved path. We also know that we are using sine and cosine as our functions, and the graphs of those functions are graphs of curves. So I want to indicate directionality as well as movement. I get to 0, 0, then I go to negative 4, negative 5.7. So that point is going to be about right there. And then 0, negative 8. And I see that I have curved back around, and I want to keep track again of my directionality of my motion. So from negative 0, negative 8, I go to 4, negative 5.7, and then back to 0, 0. So I am working to complete in the correct direction my curve. I'm going to go over to 5.7 again at negative 4. And then I finish back up at the same place I started. Okay, so there is our path of our figure skater. Is the parametric equation a function? Let's look at this next page. I'm having a hard time turning my pages. Okay, here we go. Is the parametric equation a function? Well, no. If you look at the graph, you can see that we don't have a function. It does not pass our vertical line test. But the parametric equation is made up of two functions. At each moment in time, the skater is in exactly one location. In other words, the skater's location, horizontal and vertical, is a function of time. Okay, suppose that we are going to graph the movement of a robot. And the movement of that robot is given by these two functions, where t is time in seconds from 0 to 3. So the robot is going to move for 3 seconds. We need to make a table of values and use it to sketch the robot's movement, showing directionality with arrows along our path. So we are going to have t that we're plugging in, And then we are going to plug that in for both x and y. And then we want to look at our xy ordered pairs just to keep life simple. Our domain, our input, is from 0 to 3. So we're going to do 0, 1, 2, 3. Now this is continuous motion, but we are only going to worry about those integer values, plugging them in. We come up with ordered pairs that we are going to graph on our graph. Okay, so for our first coordinate in our ordered pairs, we're using x, 6 minus 2t, so that is going to be 0. That would just give me 6. And then where t is 1, I have 4. Where t is 2, I have 2. And where t is 3, I have 0. That was simple enough, right? What about y? Well, when I plug into my y function, if t is 0, I have a negative 2. If t is 1, I have a positive 2. If t is 2, I have 6. And if t is 3, I have 10. So that gives me the y coordinates for each of these points that I'm going to plot on our graph. And these points show our movement of our robot. So our robot starts at 6, negative 2, and then it progresses through 4, 2, 2, 6, and 0, 10. And that's how far it gets in 3 seconds. Let me pull out my straight edge, because we have linear motion. Now it is a defined segment. We don't go past, we start at this specific point and we stop here, moving in that direction. This is movement along a curve, even though it is linear. From the graph above, we have linear movements. I already told you that. Okay, so we worked with those two separate equations. But by eliminating the parameter t in the parametric equation above, the parametric equation can be written in rectangular form. It's a rectangular equation involving only the variables x and t. And there's more than one way to do this, but we're going to do it kind of what I think is the most simple. We're going to start with that first equation, x equals 6 minus 2t, and I'm going to solve it for t. I'm going to solve that first equation for t. Well, that gives me x minus 6 equals negative 2t, so t equals x minus 6 over negative 2. And I'm going to take that and I'm going to substitute that in the other equation. I apologize, I hear a weed eater or something going outside again. Okay. Y equals negative 2 plus the second equation, y equals negative 2 plus 4 times t, and we have this value that we found for t. Well, let's simplify. When we simplify, we get negative 2. If we multiply this 4 in, we can simplify it right here. Minus 2 times x minus 6, which gives me negative 2 minus 2x plus 12. Which means that my equation would be y equals negative 2x plus 10 when I combine those like terms. And then what about my domain? Well, my domain started out from 0 to 3. What is it going to give me those values for t if t was from 0 to 3? Well, I can still do 0. If I plugged in 0 to 3 here, let's see, if I plugged in 3 here, 0 would give me negative 2. And if I plug in 0 here, I would have 10. And then if I plugged in 3 for t here, I would have positive 10. So that gets me to 0 to 6 is my given domain. Oh, my pen's dying. 0 to 6 is my given domain, and had not thought through that completely. So 0 to 6 is my given domain. If this is 6, this gives me a negative 2, and if this is 0, this gives me 10. So yep, that works from negative 2 to 10, and then that is the same up here from negative 2 to 10 if I go from 0 to 3 for t. If I go from 0 to 6 for x, I get the same output. This output would be from negative 2 to positive 10. This output would also be from negative 2 to positive 10. Okay, sorry about that little struggle there. Although this single rectangular equation might be more efficient than the system of parametric equations above, the advantage of the system of the parametric equations is that that system indicates to us, it indicates directionality and the relationship to time. So this single equation is going to give me the exact same output as this system of equations. They have the same output from -2 to +10. What this lacks is a feeling of the relationship to time and that directionality. So we don't see that progression. In fact, if I plug in 0, I get the 10. And when I get to 6, I'm down here at -2. So my directionality is totally reversed. And I don't have, because I'm dealing with x, not t, I don't have a sense for when things happen. So this is simpler to look at and to calculate my points, but this preserves the feeling of the motion that we're working through. Okay, we're going to do a couple more. And we are going to do them by creating some point values for our some tables. I'm sorry, I'm stuttering here. Let's look at A first. Oh, I forgot my blue pen is dead. So let's look at A first with a black pen, where we are going to be using t as the value that we plug in. We find our x and our y coordinate, and that gives us our ordered pair. Now I'm going to be quick and not rewrite our ordered pair this time. T goes from 0 to 4, so 0, 1, 2, 3, 4. And we know that each of those ordered pairs are going to be x, y ordered pairs. So I'm just going to cheat and do it like this. Alright, there's my x, y ordered pairs. This is my comma in between, so I don't have to do another column. Plugging in time to my x function, if t is 0, I have 2. If t is 1, I have 5. If t is 2, I get 8. Where t is 3, I have 11. And where t is 4, I have 14. So that's plugging each of these values for t into my x of t function. Well, what about my y of t function? I'm just adding 1 each time, so that's simple. So instead of 0 to 4, I go 1, 2, 3, 4, 5, and there are my 5 ordered pairs that I need to plot on my grid. So let's do that. It doesn't tell us what our parametric equation is, what we're mapping in relationship to time, but it's movement in relationship to time, right? So my first point is at 2, 1. My second point is at 5, 1, 2, 3, 4, 5, up 2. And then I go 6, 7, 8, up to 3. I go 9, 10, 11, up to 4. And then I go 12, 13, 14, we're going to make here, up to 5. So that should have been, I think, a straight line. I did not do a very good job. So I didn't do a very good job of guessing that point. So this motion goes from left to right and upwards. Let's do B, where again we are using t as our parameter, and we have x and y functions, and I'm going to eliminate that fourth column one more time. Here we go from 0 to 2 pi, so we are plugging in angles. Let's just do sine and cosine. Let's do 0. I think we can get away with pi half. I think we can probably get away with the pi halves. Let's try pi half, pi, 3 pi half, and we stop at 2 pi. It doesn't tell us what increments to go in. I'm guessing that we're going to try to see if we can get our motion, see if we can see it going by pi halves and not having to do pi fourths in between. We're going to keep in mind that what we're graphing are curves, because sine and cosine are graphed as that continuous sinusoidal curve. Alright, when I'm plugging in the angle for t, it's not, my parameter is not time, it's an angle. So maybe it's an angle of rotation. So cosine at 0, cosine at 0 is 1, and 1 times 2 is 2. Cosine at pi half is 0. Here cosine at pi is -1, so that would be -2, and then I'm back to 0, and then to +2 as I rotate around my cosine function with an amplitude of 2. Now let's look at, and remember, these are going to be my ordered pairs that I'm going to graph. Now we're going to look at our y function, which is a sine function, 3 sine of t, where t is 0, sine at 0 is 0. Sine at pi half is 1, so 1 times 3. Sine at pi is 0. Sine at 3 pi halves is a -1, so that makes that a -3, and then I'm back to 0. Alright, remember we have directionality, and we're going to plot our points, and then we are going to connect them with curves because we are graphing sine functions. That implies that our graph is going to be curved rather than a straight line. So I'm starting at 2, 0. I'm going to 0, 3, and then -2, 0, 0, -3, 1, 2, 3, and then back to 0, 0. So I start here, and like I said, I assume a curve because I'm graphing sine and cosine, and it looks like I have an ellipse. I want to draw arrows in to indicate directionality. All right, excellent. So, what if we want to write a rectangular equation of these curves? Remember, there's not just one rectangular equation that is going to show our parametric equation. So we're going to do 2 examples for B. We're just going to do one for A. Let's delineate our space. Okay, so we have x of t and y of t, where t is from 0 to 4. Let's start by defining x as 3t plus 2, and I want to solve that for t. When I solve for t, I get x minus 2 divided by 3, and I'm going to take that and I'm going to substitute it into my other equation. So y of t is going to be y equals x minus 2 over 3, because that's my substitution, plus 1. Now I could leave it like this, but let's clean it up a little bit. Let's say, okay, we've got x minus 2 over 3 plus 3 over, or 1, no, yeah, 3 over 3, there we go, which gives me x minus 2 plus 3, which is x plus 1 over 3. That's cleaned up. If I wanted to break it apart so that it looked more like the graph linear slope-intercept form of a line, I would have 1/3 x plus 1/3. So let's stop there. Now let's think about what our output gets us. For this original, we had our output went from 1 to 5, because if t is 0, we've got 1, and if t is 4, we've got 5. So we need a restriction here for x that gives us from 1 to 5. Well, what do I plug in for x and get 1? It may be easier to look at this one. If x is 2, then I've got 1, so 2 is going to be the least value for x. And then what would x need to be to give me 5? Well, 15/3 is 5, so if x were 14, then I get the right output. Alright, we're going to do this one 2 different ways, like I said. The first way, we are going to do substitution, just like we've been doing. So let's go ahead and let's substitute in x equals 2 cosine t. X equals 2 cosine t. So let's solve for cosine t. That gives me x over 2 equals cosine t. Then how do I finish solving for t? Well, I use my inverse function. So I take cosine inverse of both sides so that t is the cosine inverse of x half. And then I'm going to plug that in to my second function for t, which gives me y equals 3 times the sine of cosine inverse of x half. And that is my parametric function. Now my restrictions on, we're not going to look at the restrictions here. They're easier to look at on the second method. Let's look at this or over here. Okay, so I have x equals 2 cosine t, which means x half equals cosine t. That's one thing we got right here, right? X half equals cosine t. Also, I have y equals 3 sine t, which means y over 3 equals sine t. So I've solved them both for cosine t and then for sine t. Remember your Pythagorean identity. Pythagorean identity, it tells us that cosine squared t plus sine squared t is 1. So I'm going to substitute these values in. That gives me x half squared plus y third squared equals 1, which becomes x squared over 4 plus y squared over 9 equals 1, and that's the equation for an ellipse or for an ellipse, right? Okay, so now we need to look at our output, our domain. So if I've got from 0 to 2 pi, well, okay, let's look at it this way. My output is my sine function value and my cosine function value. Those are limited along any rotation between -1 and 1. So I want an output that is limited between -1 and 1. Well, what makes that happen? What would give me a -1 here? To get to this -1 here, I have to go, and you know what, we're not even going to take the time to walk through it all the way, I don't think. Anything from -2 to +2 for x is going to give me the output I want. Now to figure this out here, I would have to solve it for y squared over 9 to make sure I got -1 and +1. -2 squared gives me 4, so that's 4 over 4, right? That works. And then +2 squared gives me 4, that's 4 over 4. Then I've got 1 minus 1 there. If I plug in -2 here, that's cosine inverse of -1. I lied, this is the easier one. Cosine inverse of -1. So that's my lowest cosine function value that works. And then if I do +2 over 2, that's cosine function value, cosine inverse of +1. That's the largest cosine function value that works. I misspoke. This one was easier to look at to do my restriction on my x values. All right, one more page in these notes, and we will be done with chapter 9. I nearly took out my document camera. Example 5, using time as a parameter. Now this is kind of an application problem that we're going to look at. We are, by the way, going to skip number 7 down here at the bottom. We're going to stop at number 6. This is an application problem. We're going to need a little bit of background information that we got out of the book, out of our section. So I'm just going to give that to you here after we read our problem. Bob throws a ball straight up with an initial speed of 50 feet per second from a height of 6 feet. So when he releases the ball, he releases it at 6 feet above the ground. Now, we know that when you throw a ball in the air, it's going to go straight up, but then it's going to straight up at whatever point, and then it's going to come down and hit the ground, right? So it forms a parabolic motion. Find the parametric equations that describe the motion of the ball as a function of time. Well, so our background, it gets pretty specific with our definition. The parametric path of a projectile fired at an inclination theta, so that's my angle at which so like if I was firing a cannonball, it would go up and out this way. He's throwing the ball, it starts straight up. Theta degrees or theta radians to the horizontal, so we are the angle of inclination with an initial speed, initial speed v sub 0. That's my initial speed, velocity 0, from a height h above the horizontal. So for this equation, that's my 6 feet. I get x equals v sub 0 cosine theta times t. And then my second equation, my y equation, would be -1/2 g of t squared plus that initial velocity sine theta t plus h. So that's my system of equations in form of x and y. We've defined everything except g. it gives us t is time. We already imagined that. G is our constant acceleration due to gravity. So as gravity works on the item that is thrown on the object, and that is 34 feet per second per second. So that's my gravitational constant. Okay, so we're going to plug in what we know to get these two equations. Now, x of t is the simplest, so let's do it first. It's going straight up, so this angle is going to be 90 degrees, and cosine at 90 degrees is 0. So 0 times anything is 0. So x of t is just 0, right? And that is true because we start by throwing it straight up. So we're doing cosine of 0, where theta is 90 degrees, or pi half. Now y of t. G is my gravitational constant. That's just 32. So negative 1/2 times 32 is negative 16 t squared, plus, and then my velocity, 50 feet per second. That's v sub 0. So 50 sine of theta is 1, because pi half is 1, right? Sine at pi half is 1. So that's 50 times 1 times t, so just 50t. And then plus h, where h is that initial height above the horizontal, and he released it 6 feet up. So there's my system of parametric equations. How long is the ball in the air? When does it hit the ground? It hits the ground when the height is 0. So we're just going to set our equation equal to 0. This is college algebra stuff, right? Set our equation equal to 0. I can do a couple of things to simplify it. The easiest way to simplify is going to be to divide out a coefficient of -2. That gets my squared term positive. I have 8t squared plus 25t plus 3, and it reduces all of these coefficients as much as possible. Now this is still not factorable. There's no way I can combine factors of 8 and 3 and end up with 25 in the middle. It's not going to be a nice integer solution. Well, what do I do with a quadratic equation that does not have a nice integer solution? I use the quadratic formula. So I have x equals negative b is a negative 25. Oh, I didn't change that sign. That sign should have been negative, and that sign should be negative. I hope you were all at home yelling at me about my mistake. So I have 8t squared minus 25t minus 3, because I divided everything by -2. Okay, now b, the opposite of b, is positive 25, plus or minus square root of b squared, 25 squared is 625, minus 4 times a times c, where c is negative, all over 2a is going to give me 16. So this simplifies to be 25 plus or minus square root of 625 plus 96. 8 times 3 is 24, times 4 is 96, over 16, which is 25 plus or minus square root of 721 over 16, and nothing here simplifies nicely. Now, if I do 25 minus the square root, I get a negative answer. That's not going to work for me. So I only have the one solution where I do 25 plus the square root of 721 and then divide that by 16. And I come up with about, and we're going to leave 3 decimal places, after about 3.241 seconds, the ball hits the ground. So that's how long it travels in the air before it hits the ground. Well, what is its maximum height? The maximum height of the ball occurs at the vertex of my parabola, that highest location. This is as high as the ball gets. This is when it hits the ground. Well, the vertex of a parabola, if you think back, that x-coordinate is negative b over 2a. It's that first part of my quadratic formula. So that negative b is a positive 50 over 2a is 2 times 8. So that gives me 50/16. And I'm going to take that 50/16 and I'm going to plug it in to y. So y of 50/16. And that's going to give me the maximum height of my ball. So I have negative 16 times this squared plus 50 times 50 sixteenths plus 6. And what you should get out is that it gets to about 45.063 feet up before it drops. Now we're not going to use our calculator to check because we're not using a graphing calculator. You could plug it into decimals, I guess. Example number 6 emphasizes the fact that our parametric equations are not unique. So parametric equations are not unique. I'm going to find two different parametric equations for x equals y to the 3/2. Well, we're just going to pick a place to start. The place I'm going to pick to start first is to let x equal t. Well, if x equals t, then this becomes t equals y to the 3/2. And to solve for y, I'm going to raise both sides to that inverse power, so that's the 2/3 power, and that gives me y equals t to the 2/3. And that is true for when x equals t. So there is a system of parametric equations. There's one system. What about another system? Well, let's define x differently. Let's choose to define x as t cubed. If I let x equal t, I have t equals y to the 3/2. If I let x equal t cubed, then I have t cubed equals y to the 3/2. So that for this one, when I raise both sides to the 2/3 power, I get to y equals t squared, and that's true when x is t cubed, and that is a second system of parametric equations. Both of them represent that rectangular equation. Like I said, we're going to skip this last one. It's fine. It's just this is as in-depth as we need to go in this section.